Welcome to the Deep Dive, where we take a mountain of information and distill it down to the essential, fascinating takeaways you need to know. Today, we are strapping in for a really deep dive into the absolute cutting edge of connectivity, 6G wireless.
And here's the hook, and it sounds like something straight out of science fiction. The core intelligence that's going to manage this next generation of wireless networks. It's going to be powered by an AI inspired by, of all things, a simple microscopic roundworm.
It sounds completely absurd, but I guess it really speaks to the kind of radical thinking we need to build this future. Our sources, they paint this truly transformative picture of 6G. We're not just talking faster phones.
No, not at all. We're talking about networks capable of what's called ultra-reliable, low-latency communication, URLLC. Think responses in milliseconds.
Which you'd need for things like massive IoT, holographic telepresence, and, fully integrated smart cities where every single device is connected flawlessly.
And the complexity there is just immense. Imagine scenarios like space-integrated ground networks, all talking to AI-empowered base stations. The goal isn't just to transmit data. The network literally has to sense, anticipate, and manage its own environment in real time.
That intelligence has to come from somewhere, and that somewhere is AI. But that brings us to the fundamental problem. If AI is so essential for 6G, why aren't the powerful deep learning models we have today, the things we all hear about, why aren't they ready for this kind of prime-time dynamic environment?
And that is precisely our mission for this deep dive. We're going to unpack why those traditional models really struggle, and then we'll get into how these liquid neural networks, or LNNs, are designed from biological first principles to solve the three huge challenges facing AI and 6G.
Okay, let's unpack those. Let's start there. If AI is the key, what are the specific issues that make our current models just crumble when you try to apply them to a real-world communication system?
Well, the failures all really stem from the environment itself. It's just so dynamic. Traditional AI, it's designed around these static, clean data sets, but the airwaves are anything but.
So lay out that first hurdle for us.
The first one is the huge issue of robustness. Current AI models, they just show this massive drop in performance in dynamic environments. Think about a person just moving while streaming a video.
Right.
That user's mobility, interference from other devices, the channel conditions changing, it means the data is constantly shifting. An AI model trained in a lab under perfect static conditions, it just fails. It can't maintain performance when things change out in the real world.
So if the model's too rigid, it basically shatters the moment it sees something even slightly different from its training data. It can't operate in the messiness of real life. Okay, what's the second big hurdle?
That would be the issue of interpretability. Most people know this is the black box problem. Deep learning models can be incredibly powerful, but they're opaque. They often can't explain how they actually arrived at a decision.
Why does that matter in a 6G network? I mean, it's just moving bits around, isn't it?
It matters a lot, actually, because we're talking about safety-critical infrastructure. If an AI is autonomously managing something like spectrum resources or routing traffic for, say, emergency services, you absolutely need transparency. You have to be able to justify those decisions, make sure they're fair, make sure they're efficient.
Okay, so you need to be able to audit the AI.
Yeah.
That must solve a massive legal headache for companies trying to deploy this stuff. So we've got rigidity and we've got opacity. What's the third and maybe the most immediate problem in the field?
That is the issue of complexity. And simply put, current deep learning models are just resource hogs. They require a ton of computational power. We're talking specialized hardware like GPUs, TPUs, not just for training, but critically for actually running the models once they're deployed.
And 6G is supposed to be everywhere, right? From these huge city centers to tiny little devices on the edge of the network.
Exactly. So this high complexity makes them completely impractical for those resource-constrained scenarios, like edge computing, where power is limited and latency is everything. If the AI at your local base station needs a giant server farm to run, it just defeats the entire purpose.
So we have a really clear problem. Our AI models are too rigid, they're too opaque, and they're way too demanding. And this is where the source material just takes this dramatic turn. How do you design an AI that bypasses all that? Where does the inspiration for these so-called liquid networks even come from?
This is where we go back to biology. The designers looked at nature to see how efficient, adaptive systems handle a continuous fluid flow of information. And they found their answer in the microscopic nematode Caenorhabditis elegans.
Wait, hold on. We are modeling our most advanced wireless networks on the brain of a simple worm that's barely a millimeter long.
It is. because the C. elegans nervous system, despite having only 302 neurons, is incredibly robust. The key insight was that its synapses, the little junctions between neurons, they're continuously adapting. They dynamically reorganize in response to new inputs.
So the goal wasn't to build a bigger, more complex brain, but to build one that processes information more like a stream of water than a series of rigid, separate steps.
Precisely. And that leads to the fundamental mathematical difference. Unlike traditional networks that operate in these discrete time steps, like checking a clock once a second LNNs use ordinary differential equations, ODEs, to model things in continuous time. The network state is always flowing, like a river.
That makes the responsiveness sound so much more natural. You're always tracking the current state of things, not just guessing based on the last snapshot you took.
That continuous modeling, it allows the LNN to capture these really subtle temporal relationships that the discrete models just completely miss. And from this basic design, we get three main architectures.
Okay, let's start with the one that kind of proved the whole concept.
Right, so first you have the original. Liquid Time Constant Networks, or LTCs. These are the most flexible and adaptive, and they show that you could achieve really high-fidelity autonomy like controlling a simulated car with as few as 19 liquid neurons.
19. Just 19 neurons. That is stunningly small compared to the millions needed for traditional models. I mean, that right there solves a huge piece of the complexity problem.
It does, but, solving those ODEs iteratively, running the simulations, it still takes a fair bit of computational power, which led to the second type, closed-form continuous time networks, or CFCs.
And what was the optimization trick there?
Well, CFCs found this really clever mathematical shortcut. So instead of forcing the computer to run these intensive step-by-step simulations to solve the ODE, they developed a simple, elegant formula, a closed-form solution, to approximate the math very quickly.
Hang on, how does approximating the math still preserve that liquid quality? Wasn't that the whole point of using the ODEs in the first place?
It's a great question. It maintains the key behavioral properties, that continuous nature, but it gives you the result much, much faster. It's really a pragmatic engineering solution that keeps the benefits of continuous modeling while seriously boosting the computational efficiency. It's critical for getting LNNs onto small edge devices.
Okay, that makes sense. And what about the final configuration?
And finally, you have neural circuit policies, or NCPs. These are based on layering the liquid neurons into these distinct biological-like sections: sensory, inter, command, and motor layers. And the really critical design choice here is the use of sparse connections between these layers.
Like a streamlined biological circuit only communicating what's absolutely essential.
Exactly. That sparse design is a direct nod to how nature works, and it further reduces complexity, it speeds up information exchange, and it contributes hugely to the model's overall energy efficiency.
So we've covered the design. Let's zoom out to the so what of all this. What are the tangible benefits of using this liquid architecture? What does it actually give a 6G network that other AIs can't? I think you mentioned 5 superior features.
Yes, and these 5 benefits directly attack those roadblocks we talked about. First, as we've been saying, is just superior generalizability and robustness. Because they're built to continuously adapt, LNNs handle what's called out-of-distribution data incredibly well. So if network conditions suddenly change, a huge surge of users, new interference, the LNN just keeps on performing.
Which is the absolute core requirement for 6G's promise of reliability.
Sure.
What about the depth of its performance?
Well, second, we see enhanced expressivity. Now, this is a little technical, but LNNs generate significantly more detailed and longer latent space trajectories.
Okay, let's translate that. What does that jargon mean in practice for the network?
It means the network has a richer, more detailed memory of what just happened. It can capture and integrate that historical information much faster, allowing for these really rapid nuance adjustments. It remembers the flow of the channel conditions, not just the last static snapshot.
That added detail must help with the black box problem too.
It does. Which brings us to number 3, improved interpretability. Because LNNs are based on these relatively simple ODEs, you can actually untangle their dynamics into understandable behaviors. Researchers can use standard tools, like decision trees, to analyze the neural policies and get clear logical explanations for why a decision was made.
And you mentioned this is crucial for trusting safety-critical applications. Being able to audit the AI has to be a game changer for the industry.
Absolutely. Fourth is lower complexity, which is just essential for 6G sustainability. The mix of sparse connections from NCPs and the computational shortcuts from CFCs means LNNs need fewer neurons and way less processing power. And that translates directly into faster speeds, less overhead, and critically much lower energy consumption.
But why does lower complexity matter to me if I'm just on my phone?
Because it means the base stations run more efficiently, which is a greener solution, and the devices on the edge, like your phone, they need less power for tasks that rely on local AI, which means better battery life and faster local processing for you.
Okay, efficiency, sustainability, and better performance. What's the final feature?
And finally, continuous time precision. That ODE modeling just allows LNNs to respond more naturally and precisely to the constantly changing environment. And that precision is what you need for super accurate channel estimation and fine-grained interference management in these really fast-moving scenarios.
Okay, let's see how this all translates into practical solutions. Where are LNNs making the biggest difference right now in these early wireless applications?
We're seeing them play a huge role in systems that need to integrate data simultaneously. First, there's integrated sensing and communication, or ISAC. This is a big paradigm shift where communication and sensing functions are merged into one. The LNN is perfect for optimizing the resource allocation between those two functions in real time.
So the network is constantly talking and sensing its environment at the same time, and the LNN is managing that delicate balance.
Exactly. And the second big area is self-organizing networks, or SONs. LNNs allow the network to autonomously reconfigure itself. It can predict congestion, it can optimize handovers, all in real time without a human having to intervene. It just leads to far more resilient and efficient networks.
We have to move past the theory now and look at the actual proof from the case studies. What does the data really say about LNN performance versus the old benchmarks when things get dynamic?
The data is pretty compelling. So if you look at channel prediction using LTCs, channel state information CSI is what the network uses to predict where a signal is going to go. In real-world simulations, the LTC approach consistently got a significantly lower mean squared error MSE than traditional models like LSTM.
And lower MSE just means fewer errors. It's a more accurate prediction. Was that accuracy gap stable?
No, it actually got better as the task got harder. The sources confirmed that the performance gap widened significantly as the prediction length increased. This shows that LNNs have superior accuracy in long-term prediction, exactly what 6G needs.
That stability over time is really powerful. What about that other example, dynamic beamforming?
Yeah, that study focused on dynamic beamforming with NCPs in a complex antenna system. The test involved users whose speed was changing rapidly, from 6 meters per second to 15, then up to 30. This is a real stress test.
That's like a car accelerating hard down a street. What happened to the signal?
The LNN-based model, which uses those efficient NCPs, it quickly surpassed the traditional industry benchmark. And crucially, it maintained a superior average spectral efficiency, which just means a higher rate of data transfer across all three of those rapidly changing speed phases.
So the standard algorithm is what everyone uses for efficiency, but when the user started moving fast, the LNN was able to keep the signal locked on so much better, it proved its real-world reliability.
That quick, continuous adaptation is the signature advantage of the liquid architecture.
So LNNs seem really poised to power the AI layer in 6G, but what are the remaining technical challenges? What needs to be solved to ensure they get fully deployed?
Yeah, despite the clear benefits, there are about 4 main research frontiers. First, and maybe the most critical for 6G's strict requirements, is training and inference latency.
Time is everything. If the decision takes too long, the environment's already changed and the decision is useless.
Exactly. Researchers have to measure and optimize that inference speed, specifically the time it takes to solve those ODs, to make sure LNNs can meet the sub-millisecond real-time response that 6G demands. That might mean new hardware or better software solvers.
What's the next challenge for these massive systems?
The second is developing distributed LNNs. For huge, large-scale wireless systems, we need frameworks, maybe using federated learning, that allow for collaborative local training across millions of devices. That keep your data local, which is great for privacy, and it cuts down on the communication overhead.
So keep the learning local and collaborative. And what about when you have very little data or brand new situations?
That leads to the third area, zero-shot learning, or ZSL. Even though LNNs are already robust, we need to enhance their ability to generalize from very limited data and transfer knowledge instantly to completely new situations they've never seen before. And finally, there's multimodality fusion. Future 6G apps won't just use one type of data. They'll be integrating everything, sensor data, audio, video, text, in real time. We need to design LNN architectures that can handle all that diverse information and manage the complex synchronization issues that come with it.
This has been a true deep dive. We started with this grand vision of 6G and ended with the microscopic inspiration behind the AI that's going to power it. It seems LNNs really do solve that trifecta of robustness, interpretability, and complexity through this biologically inspired continuous times adaptation.
And if you connect this back to the bigger picture, you have to remember that the highly dynamic nature of 6G will require not only fast inference, but also frequent model retraining. The full success of LNNs really depends on solving that training pipeline latency so the network can continuously adapt its own intelligence, just like that tiny nematode.
It really makes you wonder. If the future of 6G, this ultimate hyper-connected world, relies on a neural architecture inspired by a simple worm, does the true future of AI lie in just scaling up with brute force computation? Or is it about perfecting the foundational flow and adaptability of information? That's something to think about until the next time you join us.